Hello, Chem 2 students. This is the video for Wednesday, September 30th, 2020, which is our scheduled 29th day of school for the fall semester. Of course, always keep in mind that the dates could change for a variety of reasons, but the lessons and the order of those lessons will remain the same regardless of that. So let's look at our do nows and see what today's schedule is. So today we're going to start Unit 3.1, okay, over electrons and atoms. So you're picking up the visible spectrum assignment, which will be your homework for tomorrow. You're going to need out those packets, that packet of 4 charts, the electromagnetic radiation handouts. We're going to be looking at a couple of those today. So make sure you get that out. As far as the Unit 2 exam, I do have them graded, and they're in the grade book. I still have, I think, a student or two who hasn't taken it yet, so I probably won't hand them back until tomorrow, hopefully Friday, at the absolute latest. There was no homework for today, as the assignment yesterday was a work day, and the assignment that you received yesterday, you turned in before class was over yesterday. So, no homework for today. Today we'll start the first half of Unit 3 by reviewing the electromagnetic spectrum. We had this in Chem 1. We're going to talk about some details regarding that, make sure you know them. And then we're going to focus on one region of that spectrum, which is the visible spectrum. The assignment, of course, that you picked up today will be due tomorrow. So let's pull up the notes and get started. So the light emitted or absorbed by substances has helped scientists to understand the electronic structure of the atom. All right. So we're going to kind of bridge together the Rutherford model of the atom, which is the one we left in Unit 2, and we're going to move forward to the modern atomic theory, which basically started with this right here. Okay. Electromagnetic radiation, or EMR, we talked about that in Unit 2. Carries energy through space, right, via photons. It's a transfer of energy without a large-scale transfer of matter. So EMR, or radiant energy, is transferred via massless particles called photons. All types of EMR travel through a vacuum at a speed of 3.00 times 10 to the 8th meters per second. This is called the speed of light. Right, so although we call it the speed of light, of course, which light travels at that speed, light is but one type of electromagnetic radiation, and they all, travel at that same speed. To 9 sig figs, it's actually 2.9979248 times 10 to the 8th meters per second. But we're going to stick with 3.00. All types of EMR also have wave-like characteristics, right? Those similar to water waves that are visible to the human eye. All right. Waves are also periodic in nature. Their pattern of peaks and troughs repeats itself at regular intervals of time. All right. The distances between successive peaks or troughs in a wave is called its wavelength. That's the Greek letter lambda, and it is measured in meters. Sorry. The number of complete wavelengths or cycles that a wave undergoes that pass a given point in 1 second is called the wave's frequency, which is the Greek letter V. All right, it is measured in hertz. All right, in hertz, which is actually an inverse second. All right, so let's take a look. Now you have a handout with this, but I think I'm going to free draw it and talk about the relationship between wavelength and frequency. Okay, and period. All right, so let me do that over here on the board. So let's say. Here we have a wave. Here's its initial starting point, and it goes something like so. Okay. All right. So this maximum distance from the equilibrium position to the height, so to speak, of the wave is called an amplitude. So all of these here are called amplitudes. All right? Amplitude. like so. All right. Now, if it's a amplitude in the positive direction, the up direction, we call it a peak. If it's an amplitude in the negative direction, we call it a trough. But a peak and a trough both measure amplitude. All right. So a distance between successive peaks or troughs is called a wavelength. So here's a peak over here, and so that distance there is a wavelength, peak to peak. You could measure trough to trough. You can measure anywhere in between. All right. If I have this point here and I go to the same point in the next successive wave, that is also a wavelength. Those are equal. All right. Now, let's say that this right here, we start our time here and we end it right here. All right. So right there and right there. So I want you to see that this wave has undergone one complete cycle at this point here. So see here, it's starting up from the equilibrium. It's doing its thing. And when you get back here, it's starting up on its path again. So it has cycled through one time. All right. So if this is, let's say it's equivalent to 1 second. All right. Then its frequency would be that it cycled one time in 1 second. And that we would call that then a value of 1 hertz, or 1 cycle per second. In other words, the wave cycles itself through one time in 1 second. Its frequency is 1 hertz. All right. So now let's look at another one. I'll put it up here. All right. And now we're going to do this. Not the best drawing by any means. All right. So now let's look at that. All right. So what do you notice about this? Well, if we look at the wavelength here as compared to this one, the wavelength is much smaller. All right. We have a much smaller wavelength. How about the frequency though? Well, let's look at that. So here was 1 second. Let's just make that 1 second again. All right. So here it starts on its path, and here it starts again. That's 1 cycle. And here it starts again. That's 2 cycles. And now here it's halfway through. So it's halfway through a third. So we got 2 complete cycles plus a half of one. All right. Well, now our frequency would be 2.5 hertz. All right. Or 2.5 cycles per second. How does that compare to down here? Well, with a smaller wavelength, you can cycle through more times in a given amount of time, in this case 1 second. So we end up with a larger frequency. All right? Smaller wavelength, larger frequency. Thus, wavelength and frequency are inversely proportional. That is something you must know. All right? They are inversely proportional. All right? Now, the wavelength and frequency of all types of EMR are related since all move at the same speed. The speed of light, 3.00 times 10 to the 8 meters per second. All right? Wavelength and frequency, as we just said, are inversely proportional. If the wavelength is long, like it was here, then there'll be fewer cycles of the wave passing a point in given time, in this case per second. And thus the frequency will be lower, and vice versa. So remember, two things that are inversely proportional. Their product equals a constant. We've talked about that before in regards to inverse relationships. Well, in this case, the product of the frequency and its wavelength yields a constant, as we just said, and that constant equals the speed of light, all right, or 3.00 times 10 to the 8th meters per second. So any type of EMR, regardless of type, all right, when you take its frequency times its wavelength, you get a constant, and that constant is the speed of light. Now, before we do calculation there, let's look at our EMR spectrum, all right? I have a color one here, and you are going to get a color one, or you have a color one too. Just gives you, it lets you see it a whole lot better than one that's in black and white. So let me pull that up real quick. Then we'll come back to this. Oh, is that thing beautiful or what? All right. So I just want to review with you what we talked about just now, and also a little review from back in Unit 2.2 when we were talking about nuclear radiation. All right. So here, all right, here we are showing the electromagnetic spectrum. Only now we're showing it by increasing wavelength. All right, increasing wavelength. So this is wavelength. Gamma rays, as you can see, have a very short wavelength, 10 to the minus 11 meters. All right. So this is the shortest wavelength down here. As you go through X-ray, ultraviolet, the visible spectrum, infrared, microwave, and radio. Radio waves have wavelengths of up to 1,000 plus meters, 10 to the third on up, and actually 10 to the first on up beyond that. And so here we have the longest wavelength, right? Longest wavelength. So now let's look at frequency. So here's frequency. Remember what we just said? Wavelength and frequency are inversely proportional. So with the smallest or shortest wavelength, you are going to have the largest frequency, all right? And as you can see, gamma rays have an extremely large frequency, 10 to the 20th hertz on up. What did we say in Unit 2.2 about gamma? The energy associated with gamma, right? It's extremely large. In fact, it's the most energetic, making it the most dangerous type of ionizing radiation, right? And so why is that? Well, it's because of its frequency right here. So the largest frequency also yields the largest energy, all right? And as you work your way on down, their frequencies get smaller and smaller and smaller. So radio waves have the smallest frequency and thus the smallest energy. And remember we talked in Unit 2.2, when we were talking about nuclear radiation, that radio, microwave, television waves are in here too, by the way. Radio, microwave, infrared, and visible are all non-ionizing. Remember that? All the way through here, we had non-ionizing radiation, meaning the energy isn't large enough in order to cause damage to living cells, all right? But when you get over here, UV on up, UV, X-ray, and gamma, now we're looking at ionizing radiation, which of course is something we got to be concerned about. And as you get more energetic, larger frequency, the energy associated with those types of EMR become more and more dangerous to living cells. All right. So now we are going to look at the visible spectrum. I want you to see, number one, it's very narrow. That's it. That's all the wider it is. It's right in here, around 10 to the 14th hertz, around 10 to the minus 7th meters as far as wavelength. So what we have done here is taken this very narrow range and extended it out down here, all right, so that you can see it better, all right? And so let me grab something real quick. I don't seem to have it on me, but that's okay. No worries. All right, so I want you to see then that we have extended this out. Remember, wavelength, the smallest wavelength is down here, largest is down here. All right? And if you look down here, you will see the color spectrum. All right? Violet, blue, green, yellow, orange, and red. So now wait a minute. Roy G. Biv. Of course, Roy G. Biv goes the opposite way. That goes from longest wavelength to shortest. We're showing shortest to longest here, so it's the opposite. But you say, wait a minute, Roy G. Biv, there's an I in there, indigo. All right? Well, indigo's right in here. Blue, Biv, indigo's right down in here. Whoops, can you see that? There we go. So indigo's right down in here between violet and blue, but it's not listed here. Well, indigo is not universally recognized as a color. The band of wavelengths for indigo is so narrow that in several reference books, it's not listed as an official color. We all call it the indigo, but being able to distinguish the color indigo as compared to just a mixture of violet and blue, for some people, it's impossible. For others, they say, oh yeah, there it is right there, indigo. All right, but it's a tough call. And so it's not universally recognized, but it's no big deal. All right, whether it is or it isn't, it's right in here somewhere between violet and blue. All right, so we have violet, blue, green, yellow, orange, red. And as you can see, the wavelength, now this is listed in nanometers, right? Nanometers, so that we're dealing with whole numbers, all right? In the hundreds, actually. Remember, a nanometer is 10 to the minus 9 meters, all right? So 400 nanometers is equal to 400 times 10 to the minus 9 meters. But that, of course, is not in correct format for scientific notation. So it's 4.00 times 10 to the minus 7 meters. So these are in nanometers, 400 for violet, 700 plus for red, give or take, all right? And then the others fall in between there. So you get a pretty good idea. So here's violet, indigo's in here somewhere, here's blue, but now we're getting more blue-green, then we're getting to green, then we're getting more to green-yellow, then to yellow, and then more yellow-orange, and then more orange-red, and then finally red. So, you got some areas in there where the colors are merged, and so they get a little bit different shape, all right? So, but anyway, I want you to see that the visible spectrum lays out just the way the rest of the EMR does. As you go from violet to red, violet is the shortest wavelength of the visible spectrum, which means it has the largest energy of the colors of light. Red, having the longest wavelength, again, has the smallest frequency and thus the smallest amount of energy associated with it. So, important point. Those of you that remember cameras, and then when you develop film, anybody know this? Maybe you've seen it in a movie if you don't know this personally. In the old days when they developed film, they did it in what's called a dark room. All right, so we talked about this before. Film can be chemically exposed and ruined by large energy radiation. Anybody remember what type of light they use in a dark room so they can see what they're doing? And if you said red, you're correct. Why do they use red light? Because of this right here. Red light is the lowest energy of the colors of light. And so you're not going to expose or ruin the film using red light as if you were, for example, using violet or blue light. We're going to talk about that tomorrow in terms of Niels Bohr. All right, it's an important part of his work. But anyway, so this lays out exactly the way the entire spectrum does. Smallest wavelength to largest, all right, or largest frequency or energy to smallest. Remember, they're inversely proportional. Maybe one last little tidbit here. Ultraviolet. So why do we call this range of the EMR ultraviolet? Well, it lies right next to the color violet. Ultra means beyond. all right? So ultraviolet is more energetic, all right, than violet light is, okay? Infrared. Why do we call it infrared? Well, infra means below. Infrared is the region right next to red, the color red on the visible spectrum, and it has a lower energy, all right, than the color red does. So infrared, lower red. So I don't know if you knew where those terms came from, but that's where they did. All right. Hopefully you got all that down. I hope you wrote that down. It's all stuff you got to know. All right. Let's go back to the notes and we'll do a quick example for tomorrow's homework, and we'll be set to go for today. There we go. So let's look at this example here, and then we will be finished for today. All right. So again, the product of the frequency and the wavelength, EMR, and in particular, light is a type of EMR, is equal to a constant because it's an inverse relationship. That constant is the speed of light. So C is the speed of light. That's the variable we use. Speed of light. And to 3 sig figs, it's 3.00 times 10 to the 8th meters per second. B, of course, is the frequency in hertz, which is basically cycles per second. And wavelength is in meters. The standard unit of length is the meter, so we got to make sure that our wavelengths are in meters. All right. So, first example, the wavelength of a particular type of red light is 750 decimal point nanometers. All right, 750 decimal point nanometers. That's our wavelength. What is its frequency? All right, so we're looking for frequency. So we're going to use the speed of light equation to solve. However, first of all, we need to convert nanometers to meters. Whether you move the decimal or do a conversion factor, doesn't matter to me. I'll do a quick conversion factor. But if you just want to move the decimal, that's fine. We've got to make sure we put it in proper format for scientific notation. So if we have 750 dot nanometers over 1, nanometers down here, meters up here, so that nanometers cancel. Of course, a meter is much larger than a nanometer, and it's by a factor of 9 places, which is 9 zeros, or 1 billion. So we got 1 billion, or 1 times 10 to the 9th nanometers in a meter. And when you divide that out, you get 7.50 times 10 to the minus 7 meters. All right, 3 sig figs. Again, if you also just know that a nanometer is 10 to the minus 9th meters. All right, 10 to the minus 9. It's much, much smaller. 9 decimal places smaller. As I did a little bit ago, you could just say, okay, well, this is 750 times 10 to the minus 9th meters. But again, that's not in proper format. So putting this between 1 and 10, you're making this number smaller. So we've got to make the exponent larger by that many places. So that'd be 7.50 times 10 to the minus 7 meters. So either way, you got to determine that wavelength in meters. All right. Now let's plug it in the equation. Because the speed of light is in meters per second, so the wavelength's got to be in meters. So we have 3.00 times 10 to the 8th equals frequency times 7.50 times 10 to the minus 7. Of course, we're going to divide out the wavelength to solve for B. And to 3 sig figs, it comes out to be 4.00 times 10 to the 14th hertz. 3 sig figs. All right, so And you could double check, just take a quick look at your EMR chart and see that the visible spectrum lies in that 10 to the 14th hertz range. So that is not a mistake. The frequency is very, very large. All right. So after having looked at all this and done all this, I think you can go ahead and do your assignment. Make sure you understand the terminology involving wavelength, frequency, and the relationship between the two. Also, how energy is related to that. Energy and frequency are directly related. All right, the larger the frequency, the larger their energy. So that also means that energy and wavelength are also inversely related, just like frequency and wavelength are inversely related. Make sure you remember all that. It's going to come in very handy in the coming days. So until next time, it's Mr. Keister signing off. Everybody stay safe, work hard, stay focused, and I'll catch you next time. So long, guys.